Hey everyone, today I want to make a YouTube video on Green's theorem and what's actually going on underneath it. So, in the textbook in chapter 16.4, you saw Green's theorem as this equation right here, which basically tells you that the line integral over a closed loop, which is dp dx plus dq dy, is actually equal to the derivatives of the vector field integrated over the area. So, just to clarify, in this case, our vector field f is p for the x and q for the y. So this could be our vector field pointing in every random direction right here. Now, in chapter 16.5, toward the very end, they mention Green's theorem but in a vector form. So, what they're basically saying is, now we still have this field f, and we're taking the line integral of this vector field f dot dr over this closed loop again. So it's the same closed loop as before. But now, we view the derivatives in the center as a curl expression. So, in this case, our vector field is equal to p, q, and for r, it's going to be 0. So the vector field is still located in the xy plane. It's not pointing in the z direction. Just like this. Alright, what do these two expressions have in common, and what do they mean? So, remember in chapter 16.5, when we first talked about curl, if let's say our vector field is p for x, q for y, and r for z, when you take the curl of it, you get all these derivatives over here. But for Green's theorem, it's in 2 dimensions only. So how do we but curl turns out to be a vector in 3 dimensions. So how do these two expressions work out? What happens is in this expression, we set your r here over to be 0. So what happens is there is no vector field pointing in the z direction. That means this expression will be 0. dq dz will be 0 because there's no vector field pointing outward into the z direction. dp dz is also going to be 0 because there is no change of the p expression into the z direction. Remember that the vector field is only placed in the xy plane. There's no portion of the vector field in the xz plane, and there's no portion of the vector field in the zy plane. Next, our r is 0, so this is a constant. The derivative of a constant is 0. So dr dy is 0, and dr dx would also be 0. What are we left with here? Well, we're left with this expression right here. dq dx minus dp dy. That's the same expression right here. But there's one more caveat. This is an expression in a vector field, in a vector form. So, what we're left with here is we still have these two derivatives. We still have these two derivatives in a vector form. But in this case, we treat it as a scalar value, and then we integrate it over the entire region A. So how does this work? In the second example here, notice that when you compute the curl, which turns out to be this vector form, we dot it with k. So what is k? Remember that k is your little vector pointing in the z direction. So your k vector would equal to 0, 0, 1. That means when you dot these two expressions together, curl of f dot k, you're going to get 0, 0 dq dx minus dp dy dot 0, 0, 1, which turns out to be dq dx minus dp dy. And now we get the scalar value in here. So these two expressions, curl of it f dot k and dp dq dx minus dp dy, are the same thing. But what is the meaning behind this? Why do we need curl? How you want to think about it intuitively is, in this case, we have a vector field, f, and we're taking the line integral of this vector field over a closed loop. And it just so turns out to be that the curl of the vector field over the area, when you take the double integral and sum up all the little curls, here's our little curl with its curl vector pointing upward. Again, here's our little curl. Here's our curl vector pointing upward. When you sum up all these little curls, it turns out that when you sum up all these little microscopic circulations, it is equal to the macroscopic circulation, which is just the line integral on the outside region. So, how you can view this is that if the little curls are all rotating in the same direction, whether they be clockwise or counterclockwise, they cancel out right next to each other. And so you can just view the portion outside of the curl along the boundary region as your final value. So in this case, this is our two-dimensional curl. This is our two-dimensional curl expression. And we're doing the same thing over here. So we can pretend to have a z-axis over here, but our z-axis won't have anything. And so this is basically still a two-dimensional form of this expression right here. Now, I would like to give 3 intuitive examples for helping you understand the curl over the area for the microscopic circulation versus the curl versus the macroscopic circulation along the line integral. Now, these examples aren't going to be very rigorous. In fact, they're going to be qualitative, but I just want to give you an intuition behind the actual theorem itself. So, let me erase all of this, and I would like to proceed with the first example. So, for the first example, what are we going to have here? I'm just going to draw this in 3 dimensions, but you can view this expression as the xy plane only. This is our z, this is our x, and this is our y. So, let's say we have 4 little rectangular circulations over the area. So our first little circulation box would be this. So this is our first circulation. It has a curl vector going upward. And again, here is our second little rotational box over here. And our third, and our fourth. So these four all have a rotation upward. And so you can depict this as a curl vector all pointing upward. I won't draw for the last two, but here's your curl of your vector field. And now your vector field is in, just to clarify, your vector field only has two-dimensional components. For the third dimension, z, is going to be 0, which means the vector field is located in the xy plane only. Now, let's view the sum of the curls over the surface. So, let's say we look at the area integral. So, let's say we look at this first. If you notice over here, we have a positive curl value. So in this case, since they're all pointing in the same direction as the z, each square, curl of f of each square is positive. So that means when you sum up the curl dot the k vector, or in this case the derivatives, they're going to be positive. And so this expression right here is also going to be greater than 0. Alright, we've seen this. Now, this is your curl of f. Let's say we take the line integral over the region instead. So just to clarify again, your little black arrows, this is your f. This is what your vector field looks like. Your curl of f, because your f here only has dimensions in x and y, so we have all these little circulations over the xy plane. Your curl of f, as we've seen earlier, points into the z direction here. And by dotting it with k, you get the scalar value. Now, here's the fun part. Let's take the line integral and verify that it's also a positive value. So, let's take our line integral. I'll trace it by blue. Remember that for Green's theorem, we're following the positive orientation. So we're moving in a counterclockwise pattern. If this is our little path vector, dr, when you dot it with the direction of the black arrow right here, these two are in the same direction. It's going to be positive. Let's move on to the next little square. These two are also pointing in the same direction. That means it's still positive. And it will remain positive for all values along the macroscopic circulation, because these two vectors, the field f vector and as well as the dr vector, are always going to point in the same direction. That means your line integral dp dx plus q dy, which is the same thing as f dot dr, is also greater than 0. Notice that in this case, I chose all the circulations to not only be in the same direction, but also have the same magnitude of rotation. What do you guys notice here? If let's say we look in the center, this arrow right here is pointing this way. You have the other arrow pointing in the opposite direction. And they have the same magnitude but in the opposite direction. So you can view them as these little arrows actually canceling out. So these two sets of arrows cancel out. these two arrows, one points up and one points down right here. So that means they also cancel out because they have the same magnitude. All right, same case right here and same case right here. All these four arrows cancel out. What do you notice now? You notice that the internal circulations cancel out. And so you're left with this giant circulation on the outside. Your little microscopic circulation for each little infinitesimal area cancels out. And all you're left with is the giant macroscopic circulation for the line integral right here. Cool, right? Let me move on to the next example where I'm going to make sure that we have rotations in different directions. But even if so, Green's theorem still works. So, let's keep our vector field. Let's keep our x, y, and z axis. But now I'm just going to have two squares. So we're going to have one square that rotates this way like before. And we're going to have the other square rotate this way. Now, in this case, these two are rotating in opposite directions. The first one is rotating counterclockwise, while the bottom one is rotating clockwise. That means your curl vector here will point into the positive direction in the z-axis. But the one on the bottom, because the direction is in the clockwise direction, its curl vector is actually going to point down into the negative z direction. So let me draw that right here. Let's still take the line integral over the surface and verify that it works. But let me take the area integral first. So, we notice that when you do this curl of f dot k, here I'm going to use this expression instead. These two are the same, but I want to use this one because it's a little easier to explain using the second expression. So, when you have a rotation at a certain point in a vector field, your curl of vector f will have a certain magnitude. Now, remember that this is your vector k. K is equal to 0, 0, 1. And when you have a rotation in the same magnitude in a counterclockwise direction, this is pointing downward. So, let's say we sum up the first circulation first. You have this certain vector times k. Now, these two are pointing in the same direction. So, the red is your curl of f, and the black is your k vector. They're pointing in the same direction. So when you take the dot product between them, when you're summing up the dot product over the area, you have your cosine or your angle between them is 0. So that means your cosine is 1 here. Next, let's add up the expression for the second circulation. So, what does the second circulation look like? You have a rotation in the clockwise direction. So your curl vector is pointing down, but your k vector is pointing up. That means the angle between them is 180 degrees. So, through the dot product expression, you have cosine of 180 degrees. This evaluates to -1. So, when you add them up, you have a curl of k, the magnitude of curl of f times the vector k. But in this case, you have a -1. That means these two expressions cancels out, and you end up with a final value of 0. So this is 0. Your double integral over the area right here is 0. Let's take the line integral and see if this qualitatively follows the same thing. So your line integral right here is depicted by blue again. And again, we're choosing a positive orientation. And then we're following this little vector, dr, over the line integral. So, in the first case, your black vector for your vector field is pointing this way. Your dr vector is pointing this way. These two are pointing in the same direction, and so you have a positive value. So let me just denote this by f1 times dr. I know dr is not very rigorous here because it's actually an infinitesimal vector, but I just want to show you what's actually going on. Now, we go down this way. Your dr vector is pointing this way. Your field vector is pointing, again, also pointing downward. That means this value is positive right here. So, when it points downward, for this segment in space, actually, let me just focus on individual segments right here. So for your segment in space right here, these two are again pointing in the same direction. So that means your value for this area is going to be positive. So you'll have a positive number for this region in space. But if you go downward again, what do you notice this time? This time, your field vector f is pointing upward, is pointing in the opposite direction as your dr vector along this region. And because these two vectors for f have the same magnitude, that means when you evaluate this expression, it is the same negative number as before. So when you sum up the positive number right here of the dot product and the negative number of the dot product, they turn out to be 0. Next, let's take a look at this. Here, our field vector f is pointing toward the left, but your dr is going toward the right. That means the dot product of them is, again, a negative value because your angle between them is 180 degrees. So, for this region, you get a negative number again. And notice, the length of this arrow right here and the length of this arrow are the same. So, in this case, you get a positive number. But in this case, you get a negative number. And because these numbers are the same, when you add up this portion with this portion, you get a sum of 0. Same thing for the very last side. Because you have the same magnitude of the vector field f pointing this way in the direction of dr. But in this case, you have the same direction, same magnitude of f pointing downward, and so your dr and your f are again 180 degrees apart. That means these two regions, again, cancel out when you add them together. And so, your line integral turns out to be 0. This fits our expression right here over the area. And so Green's theorem works yet again for this scenario. Let me do one last scenario. This scenario is one where we have two different circulations in the opposite directions, but the magnitudes of the strengths of the circulation are different. Again, we'll choose our x, y, and z. This time, we have a rather weak circulation in the counterclockwise direction. So, as a rather weak circulation, I'm going to denote this with rather short arrows. Next, I'm going to draw a rather big circulation in the clockwise direction. So here's our rather strong circulation, like this. Okay, again, we know our curl vector is pointing upward. But this time, your curl vector, due to the small rotation in a counterclockwise direction, only has a fairly small length. Your rotation on the bottom is going to have a very large curl vector pointing down. This is going to be I'm going to denote this as a very long and a very thick arrow. Now, let's take the area integral again over this region. So, when we do curl of f dot k over dA right here, we have this short vector, curl vector, times the normal vector k, which is just the unit vector. Now, you end up with this magnitude of curl of f. Let me denote this by 1 for this smaller region right here, times k. And the cosine between them, again, is 0. But we're going to add the curl of f 2. This is the length of a very negative arrow, pointing downward. Remember that it has a much larger magnitude than this arrow right here. Now, you're going to have a very large negative number. That means when you add up these two examples, your final answer is actually going to be much smaller than 0. So you would end up with a very negative number. Okay. What happens if we take the line integral? How do we verify this? Let's take the line integral over this area. So again, we're moving in a counterclockwise or positive orientation. So here's our line integral going this way. In this case here, notice that we have a rather short vector f pointing in this direction. So our dr and our f are pointing in the same direction. We have end up with a small negative number right here as a result of the dot product. So we have a small positive number. In this case, your vector field f is pointing downward. And your dr vector is also pointing in the same direction. So this is going to turn out to be, yet again, a small number. A small positive number. Now, For the bottom segment, you have a very large vector field arrow pointing in the opposite direction of your dr vector. This results in a very large negative number. When you add up a small positive number with a large negative number, your net sum is going to be a negative number. So, your total is a negative number. Do you see that? Next, let's move on to the bottom part. Again, we have a rather large vector field arrow f pointing in toward the left, but your dr vector is going toward the right. That means you end up, for the bottom portion, you end up with a very large negative number. And for this case, it's the mirror case of this right example. So again, for this part, you're going to end up with a negative number as the total sum. So we have a negative number over to the left. We have a negative number over to the right. For the bottom, we end up with a large negative number. And for the top, we end up with a very small positive number. When you sum up all these four values, you're going to end up with a net negative number. That means your line